In this lesson, we will get into a bit more technical detail on factors that influence the collision forces for a collaborative robot. Some of these factors, such as mass and velocity, are fairly obvious. However, some other factors, such as reflected inertia and the control system design, are not so obvious. ISO 15066 refers to effective payload in several places. We will explain the items that contribute to effective payload. Also, mechanical design choices, such as gear ratios, can have a large effect on collision forces, and certain kinds of speed reducers are not very well suited to collaborative robots. We have described the use of area or region sensors to slow down or stop robots when people enter the collaborative working volume of larger robots. But for robots that fall under the category of power or force limiting by inherent design or control, the robot control system can have a large effect on collision forces, and we will give an example of how this works. There are three major factors that determine collision forces. These are the motor torque applied during the collision, the kinetic energy of the robot, and the distance to decelerate. For many robots, during a collision, the motor torque will spike to its maximum as the path tracking error suddenly increases. However, it is possible to limit motor torque during a collision, as we will explain later. The kinetic energy of the robot and its payload is defined as 1/2 of the effective mass times the square of the velocity. Note the energy goes up with the square of the velocity, so doubling the velocity means 4 times the collision energy. Finally, the distance to decelerate has a major influence on collision force. Airbags have been added to automobiles to provide a cushion of several feet to allow people to survive collisions at highway speeds that otherwise would have killed them. In a similar manner, adding foam to a robot structure or to a rigid surface in a work cell can add many additional millimeters of travel for deceleration, and also spreads force more evenly over the colliding objects. This can be very helpful, for example, in protecting the human hand, which has a lot of delicate bones. Imagine being hit by a wooden baseball bat or a foam Nerf bat. The effective payload includes the actual payload, the mass of the tool or end effector attached to the robot to carry the payload, the inertia of the robot computed as a mass at the radius of impact, and the forward reflected inertia of the motor and drivetrain computed as a mass at the radius of impact. In 1983, General Motors performed a study on the weight of all the parts in an automobile as part of a program to define the specifications of a robot for assembly. GM found that 95% of the parts in an automobile weigh less than 5 pounds. Even though there are a number of large, heavy parts in a car, when you consider the electronics, the instrument panel, the door locks, the brake system, the fuel injectors, the pistons, etc., the vast majority of the parts weigh less than 5 pounds. However, because small parts were easy for people to handle, most robots in the automotive industry were developed for large, heavy parts. A lot of small part assemblies were outsourced to low-cost labor in Asia. Today, the labor in Asia is no longer low cost, and as a result, there is a rapidly increasing interest in using robots to handle the assembly and testing of small parts in the US, Europe, and also Asia. However, in the US and Europe, we often still see powerful, large robots used to handle small, lightweight parts. Not only is it difficult and expensive to make these large robots collaborative, they waste a tremendous amount of energy. A person consumes about 100 watts of energy, as does a small part collaborative robot designed to handle a few kilograms. However, a 10 to 20 kilogram payload robot consumes 1,000 watts of energy, most of which is dissipated as heat energy. For 100 robots working in a factory, if the larger robot is selected for a job that a light payload robot can accomplish, the factory will be wasting 90,000 watts in electricity and will have to remove this energy with the cooling system. Perhaps the least understood element of effective mass at the end of the robot is reflected inertia. Reflected inertia is the inertia of the motor and the high-speed part of the speed reducer multiplied by the square of the gear ratio, as seen at the output shaft of the speed reducer. The reflected inertia can then be translated to an equivalent mass at the working radius of the robot, where this equivalent mass equals the reflected inertia divided by the square of the radius of the rotating joint. Here, we compare the reflected inertias for the exact same motor for two robots which have dramatically different gear ratios. This table is for the PF400 robot, which has a timing belt ratio of 5:1 for a 200-watt motor. The square of this ratio is 25, and the equivalent mass at a 400 millimeter radius is an insignificant 3 grams. Here is a table for a small harmonic drive robot. The harmonic drive gear ratio is 160:1, and the square of this ratio is 25,600. For the exact same 200-watt motor, the equivalent mass at 400 millimeters is 5.9 kilograms, which is 2,600 times the equivalent mass for the low ratio robot. Note, this is just for one joint, and typically 2 or more joints will be involved in a motion. This reflected inertia equivalent mass at the working radius becomes part of the effective mass in a collision. So harmonic drive robots will tend to have much larger collision forces than low ratio robots.